So in this video, I want to discuss experiment 11 on Charles's law. This is one of the gas laws that we see in chapter 11. Now, there's no video showing you the data that's seen here. Instead, I provided links to a demonstration of Charles's law on YouTube, as well as I found a couple of examples, I found one video that had some background information and a couple of examples for Charles's law calculations as well. And all of those videos are available on Moodle. What I want to do in this video is really just sort of lead you through the data analysis and then just talk about a few things with the calculations that you see at the end of this lab. And so let's just do a little bit of background on Charles's law. This is the one where it showed that the volume and temperature of a gas, they're proportional to each other. Now, I'm going to let the lecture videos cover this material in detail, and here I'm just going to hit the highlights that's associated with this lab. So I would encourage you to watch those lecture videos on chapter 11 before doing this lab. Now, this proportion statement between volume and temperature, it can be rearranged and kind of put in the form of an equation. And you always see it like this. Well, one of the forms anyway. If these two are proportional to each other, if you move temperature onto this side of the expression, then what happens is that no matter what volume and temperature combination you're dealing with for a sample of gas, if you divide those two values by each other, you should come up with a constant, just a number each time. And you actually see that in this lab. Now, the three different samples that we use for this lab: boiling point or boiling water, tap water, and then ice water. Now, the temperature scale for the thermometers that we have in lab, they're in Celsius. Now, one of the big problems that you encounter with any of these gas law calculations is that the temperature always needs to be in Kelvin. Okay, so what you have to do first off is actually convert the degrees Celsius to the Kelvin value. And we'll use this equation here. Right, so for example, to go from degrees Celsius to the Kelvin line here, so 0.5 plus 273.15 gives me 273.7 Kelvin once I round off properly. Right? This is an addition type calculation. And so when you figure out the rounding issues for it, you use the decimal places here. And we'll just apply it as is. The data's here, 10th position, so I'm going to keep my final answer in the 10th position here. So notice I am generating 4 significant figures total in this line here. And that's relevant for this last calculation. Now, these two steps here are closely related to each other. Really, the only thing we're looking for here in this row is the physical setup of the mathematical expression, volume divided by temperature. In this case, it'd be 91.1 milliliters divided by 273.7 Kelvin. And then you do that math to then come up with K. So this is going to be that K value here. And all of these values should be the same because this gas is following ideal gas formula, the ideal gas relationships between temperature and volume and pressure, etc. If you've watched the lecture videos all the way through, when it talks about the ideal gas equation, you always convert it to liters, but you may leave it in milliliters here when you're doing the Charles's law. Again, the only thing you have to do here is to make sure that the temperature is in Kelvin. And again, you do that for any calculation in chapter 11. I'll let you fill out the rest of these blocks here. Let's look at another thing that we're going to do with this data. We're going to graph this data. So the graph is already provided for you. And notice even the marks are given to you. Okay. Notice the units, milliliters and degrees Celsius for this example. So the x-axis is degrees Celsius. Where do we see that in the data? It's right here. So this is the x-axis. And then the milliliters right here is going to be the y-axis. So like, for example, the first data point would be 91.1 and 0.5. Right, I mean, the scale here is pretty tight. 0.5 is basically 0. Okay, so I'm just going to put the mark on the line. And then notice the lines here on the milliliter scale, it's actually increasing by 5 milliliters each time. That's 80, 85, 90, 95, 100. So 91 is somewhere just above that line there. So my first data point is right there. Once you plot the other two data points, then you're going to generate a straight line. Okay, so then you'll connect the lines together. And take it all the way down to the bottom here, where it intersects the y-axis, or the x-axis, I should say. And then you're going to use this line on this graph to then predict and answer these questions on the next page. Oh, and just notice there's this weird typo all the way through this lab. It should be, of course, degrees Celsius. I'm honestly not sure what happened there. And the last thing I want to look at, actually the two problems on the last page here. And let me just sort of set this up just a little bit. I don't want to do a lot with it. You know, we said V divided by T equals some constant, and that constant is the same no matter what combination of volume and temperature that you're dealing with. So what that allows us to do is to set up these little proportions. And that should be 1 there. Now when you look at this problem here, what it's asking for is the new volume of the gas after the temperature changes. This new volume is actually V2. Okay, so you'll solve for V2. I'll do that in just a second. So that means that this volume is V1. And it's originally at 25 degrees. So this is actually T2, but I'm sorry, this is actually T1, but notice it's in Celsius. You need to convert it to Kelvin first, okay? And then this is going to be our T1. T2 is this guy. Again, please convert it to Kelvin first, otherwise the calculation won't work here. And that's going to be T2. So V1, T1, T2, right? These are all numerical values. You're going to solve for V2. Okay, so this is our target. Let's just walk through the algebra here. To rearrange this type of proportion, what you do is something called cross multiply and divide. So what cross multiply is doing is that. Okay? You're you're multiplying the numerator on one side by the denominator on the other side. And notice what happens when you do this. When you cross multiply, you get rid of the fraction look of the expression. You get everything on the same line. And then that finally allows you to solve for V2 in this expression. So again, it was, cross multiply and divide. All right, so this was the cross multiply part. What's the divide part? Well, you divide by the thing that is, associated with V2. All right, you want to solve for V2. You want to move T1 onto the other side. Well, your basic setup in any kind of algebraic manipulation is, as long as you do the same mathematical operation on both sides of the equal sign, then you haven't violated the equality, if you will. You haven't messed up the equation. Because what happens when you go T1 divided by T2? Well, T1 just cancels from this side and it appears on that side without, again, messing up the mathematical expression here. Let me rearrange this to make it look a little cleaner. And now you're ready to, plug and chug these values into this expression. Again, just be careful. T2 is going to be up top. T1 is going to be on the bottom. Make sure it's in Kelvin. And you're good. Last thing I'll say down here, I won't go through the full spiel. still convert things to Kelvin. And then what temperature? Well, this is, you got to solve for T2 in this example. But you do it the same way that we did it here. Just please note, when you actually solve for T2, that is going to be in Kelvin. And then look, it actually wants the final answer in degrees Celsius. So you want to take the Kelvin, subtract the 273 from it to get your degrees Celsius. And that's all of experiment 11. Okay, thanks.